There's an old saying, a piece of folk wisdom passed down through generations, that a watched pot never boils. It suggests that our anticipation can make time feel like it's standing still. In our everyday world, watching something doesn't change it. We observe, we learn, but the act of observation itself is passive. But in quantum mechanics, the rules are different. Observation can freeze change itself, defying our everyday intuition. A phenomenon called the Quantum Zeno Effect, a mind-bending concept that challenges our understanding of reality. Imagine an unstable atom destined to decay, a ticking time bomb at the atomic level. If you measure it repeatedly, constantly checking its status, you can actually prevent it from decaying, holding it in a state of suspended animation. It's as if your gaze presses pause on reality, freezing the atom in its initial state. This effect challenges our assumptions about time and change, forcing us to reconsider the very nature of observation. Showing that the quantum world plays by different rules, operating on principles that defy our classical intuition. The Quantum Zeno Effect is rooted in the measurement problem, one of the deepest mysteries in quantum mechanics. Observing a quantum system forces it into a definite state, collapsing its wave function from a range of possibilities into a single reality, and rapid, repeated measurements can lock it there, preventing it from evolving. It's like constantly hitting save in a video game, preserving your progress at every moment, never letting your character move forward, trapping them in a perpetual state of pause. This isn't just theory, confined to the realm of abstract thought. It's a tool for controlling quantum systems, giving us unprecedented control over the building blocks of reality, with real-world applications from quantum computing to advanced sensors, revolutionizing technology as we know it. So, let's explore how simply watching can freeze time at the smallest scales, and the profound implications this has for our understanding of the universe. And to understand this, we'll start with a paradox from ancient Greece, a timeless puzzle that sets the stage for our quantum journey. Imagine an arrow soaring through the air. Zeno of Elea, the ancient Greek philosopher, posed a perplexing problem. His arrow paradox claimed that an arrow in flight is actually motionless at every single instant. In classical physics governed by Newton's laws and predictable trajectories, this is just a thought experiment, a puzzle to untangle. But when we delve into the bizarre world of quantum mechanics, where particles can be in multiple states at once, it becomes a mind-bending reality. Let's replace the arrow with an electron, buzzing around an atom in a high-energy state, eager to jump to a lower energy level. If you measure the electron's state, you force it into a single definite state, effectively halting its natural evolution, freezing it in time. It's just like Zeno's arrow, seemingly frozen in mid-air, its motion suspended by observation. After each measurement, the electron's potential journey, its transition to a lower energy state, effectively resets. Now, imagine you keep measuring the electron's state, doing so rapidly and continuously. It never gets the chance to transition to that lower state. Each observation effectively snaps it back to its initial state, preventing any change from occurring. This bizarre phenomenon is known as the Quantum Zeno Effect. Relentless observation, like keeping a constant watch, effectively traps a quantum system in its initial state. It stops its natural evolution, preventing it from changing or decaying as it normally would. The quantum world isn't just a passive stage, it actively responds to our interaction, to our act of observing. By watching, by measuring, we become an integral part of the story, actively shaping what happens next in the quantum realm. The paradox that once puzzled ancient philosophers, a seemingly abstract thought experiment, is now a tangible physical reality for quantum particles. In quantum mechanics, observation isn't a passive act of witnessing. It's a powerful force, capable of influencing the very fabric of reality. The more we look, the more frequently we measure, the more we exert control over the quantum outcome. That's the strange and somewhat unsettling power of the Quantum Zeno Effect, a testament to the bizarre nature of the quantum world. In the realm of quantum mechanics, things aren't always as straightforward as they seem in our everyday experiences. Measurement isn't a passive act of simply observing what's already there. It's far more involved. Before we take a look, before we make an observation, a quantum system exists in a state of superposition. It's a fundamental concept. It's like a cloud of all possible realities existing simultaneously, a cloud of possibilities. This state is mathematically described by what we call the wave function. But the moment we introduce a measurement, the instant we try to pinpoint something, the wave function undergoes a dramatic transformation. It collapses. It collapses into a single, definite state, a concrete reality. The very act of looking forces the quantum system to choose one particular reality out of the many possibilities. Now, if left alone, a quantum system evolves in a smooth and predictable manner, with probabilities gently shifting and changing over time. But measurement abruptly interrupts this natural flow, essentially resetting the system back to a known state. To illustrate this, imagine an atom as a ball, slowly rolling down a hill. It starts from an undecayed state and progresses towards a decayed state. Now, each measurement we make is like someone picking up the ball and carefully placing it back at the very top of the hill. So, if we make frequent measurements, it means the ball never really gets a chance to roll very far down the slope. In essence, the system is held in place, and it never truly changes. This is a demonstration of the Quantum Zeno Effect in action. It's the repeated collapse of the wave function that effectively prevents the system's natural evolution. Therefore, measurement isn't just a passive act of observation, it's an active intervention that shapes the reality we perceive. So in the quantum world, the observer is inextricably linked and always part of the final outcome. And the more often we choose to measure, the more we effectively freeze the quantum system in its current state. That's the truly paradoxical power and the profound implications of quantum measurement. The Quantum Zeno Effect relies on a subtle mathematical fact. For very short times, the probability of a quantum system changing is proportional to the square of the time elapsed. This means that in tiny intervals, almost nothing happens. If you measure the system after each tiny interval, you reset it to its starting state. Repeat this process rapidly, and the probability of change becomes almost zero. It's like taking a step into the road, then instantly jumping back, never giving danger a chance. Frequent measurements exploit this slow start, freezing the system before it can evolve. This isn't just theory. It's a method for controlling quantum systems. In quantum computing, the Zeno effect can protect fragile qubits from decoherence, acting as a shield against noise. By watching carefully, we can preserve quantum information and guide its evolution. The Quantum Zeno Effect turns observation into a tool for quantum control. For every effect, there's often an opposite. The quantum Anti-Zeno Effect shows that, with the right timing, measurements can speed up change instead of freezing it. If you measure at just the right intervals, you can nudge a quantum system to decay faster, like stirring a pot to make it boil. The Watchdog effect is a related idea. Continuous, strong interaction with a system can also freeze its evolution, not just sharp, discrete measurements. Environmental watching, like constant collisions with air molecules, can force quantum systems to behave classically, but engineered interactions can protect them. By designing the right kind of watchdog, we can shield quantum systems from unwanted noise. These effects show that measurement isn't just about conscious observation, but any strong interaction. The Zeno and Anti-Zeno effects reveal the subtle power of timing and interaction in the quantum world. Sometimes the best way to control a system is to watch it, or not, at just the right moments. The Quantum Zeno Effect was first described in 1977 by Misra and Sudarshan, inspired by Zeno's paradox. But theory needed proof. In 1990, Wayne Itano's team at NIST performed the first definitive experiment. They trapped beryllium ions, cooled them, and used lasers to watch their quantum states. Frequent measurements kept the ions in their initial state, confirming the Zeno effect. Since then, the effect has been observed in photons, superconducting circuits, and even molecules. Each experiment refines our understanding and expands our control over quantum systems. These aren't just academic exercises. They're building blocks for quantum technology. The ability to freeze, steer, or accelerate quantum evolution is essential for the next generation of devices. The Zeno effect is now a practical tool, not just a philosophical curiosity. It's a testament to how far we've come in mastering the quantum world. And it all started with a simple question: what happens when you watch too closely? The Quantum Zeno Effect is revolutionizing technology, especially quantum computing. Qubits are fragile, easily disturbed by their environment. The Zeno effect lets us pin them in place, suppressing errors and preserving information. This is vital for building reliable quantum computers and is a key part of quantum error correction. The effect also boosts the sensitivity of quantum sensors, like atomic magnetometers used in medical imaging and navigation. In chemistry, Zeno-like control can steer reactions, favoring desired outcomes. In quantum optics, it helps create reliable single-photon sources for secure communication. Wherever we need to control quantum evolution, the Zeno effect is a powerful lever. It turns the observer into an architect of quantum reality. Does nature use the Quantum Zeno effect? Some scientists think so, especially in quantum biology. Birds like the European robin may sense Earth's magnetic field using quantum entanglement in their eyes. The radical pair mechanism suggests that Zeno-like effects could protect fragile quantum states, making a quantum compass possible. The environment, usually the enemy of quantum coherence, might act as a protector through constant Zeno-like interactions. If true, life itself may have evolved to harness quantum control, using the Zeno effect for survival. It's a reminder that quantum principles may be woven into the fabric of life. The Quantum Zeno Effect's journey from ancient paradox to modern technology shows how observation shapes reality. It demolishes the idea of a detached observer. In quantum mechanics, we're always part of the outcome. This principle is crucial for building quantum computers, secure networks, and ultra-sensitive sensors. The Zeno effect and its relatives help us fight decoherence, the main obstacle to quantum progress. It's a key to unlocking a new era of technology and understanding. So next time you watch a pot boil, remember, in the quantum world, your attention really does matter.